Okay, here is a video to go through the process of plotting some G2 data, and hopefully a lot of the stuff that's covered here can be applicable to lots of types of plotting. We're going to be using Python through Spider, and then I'll kind of walk through how to plot some data. So for this data set, this is what we want it to kind of look like. The regular kind of G2 plot for a single photon emitter. And there's two main characteristic parameters for this function. One is the kind of width of this dip, which we kind of call the lifetime. Here I've just denoted by this value b, and you can see when the value is low, you have a thin dip, and when the value gets higher, the dip sort of flattens out. And then the other main parameter for the kind of most basic form of this function is where the dip dips to, and that's I've just called this other parameter a, which is this one here. So ideally we want it to go all the way to 0, and that corresponds to a purity of 1. But for noise and other sort of extraneous photon events, coincidence events, it might be less than 1. So then the dip would sort of get higher. And in the case that it's over 0.5, then it's probably the case that it's not a single photon emitter. So for this purpose of this video, I will just be looking at these two parameters. But then there's other things, like if you have sort of metastable systems, states, or some kind of other effect which will produce sort of bunching in other parts of the plot, then we can add in other elements to the function. But for this purposes, this will be sufficient. So here's a data set that I collected, and if we click on it, you're going to see that it consists of 2 columns, and the first line is just some strings, so some words, time and the counts of the labels of the columns, and then the column themselves consist of just numbers, and then in between the column is some kind of spacing thing or a delimiter. Sometimes this will be a space, sometimes a comma, sometimes a tab, and then this just kind of goes on like this. So the goal is to just take this text file and plot it, and then sort of produce a nice image that way. So here's the Spider software interface. So on the left here is the editor where we write our scripts, and then on the right is a console where we can sort of see some output and do some scratchpad sort of stuff. And then up here, you might use the plots to visualize. I personally don't like to see the plots thing there, so I like to have the plots plotted inline. So it's kind of a bit more cleaner, but that's just the way that I like it. So the first thing I would do is I know that I want to use some sort of basic functionality that is consistent across all these kind of scripts that I write. So I'll go to the wiki, the Quantum Materials Group wiki, and download the latest version of this big collection of functions that we've written. And this just consists of lots of definitions of functions and a kind of short explanation of how they work. So one way that we can sort of get this onto our computer is just to copy the raw contents. And then in here, I'll just sort of paste this in like this, copy paste. And now it's all there. So I'll save this, actually, I want to save it as Control-Shift-S, save as. So I'm going to go to the folder where my data is, and I'm going to call this ehd underscore functions.py. Okay, so now in this folder, that script is, or this Python script is living in this folder. It's not completely necessary that this lives in the same folder as your data, but it's handy to have it in a kind of similar project folder. So in this video, the definitions the functions that I'll be using mainly are this one, load files, and then this one, save figure, and then some others that I'll talk about. So the next thing I would do is I would create a new script, which is the script that I want to use to actually plot these data. So what I would usually start off with is to import the NumPy module or library. And this one contains all the things that we can use to do operations on arrays, vectors, matrices. And usually our data comes in just rows and columns of numbers. So this is the package that I find useful for doing that. And instead of referring to all the functions within the NumPy library by the full name, we can just save ourselves some trouble and shorten it to this. So we're just kind of naming the library from NumPy to MP. And similarly, if we want to do plotting, then the library for that is matplotlib. So import matplotlib as PLT. So these are sort of public libraries that other people have created and maintained, and luckily us, we can use them. And now this is where we want to import our own functions from this library. So we want to do import from. We don't want to import the whole of everything that's in here just yet. So we can do from PHD functions import load files and save figure. I think that's the way that's spelled. So load files, load underscore files, and then save underscore figure. Yeah, okay, that's right. Okay, and then I like to separate these things in cells. So I'll do a cell here like this. So now I can run this cell individually by pressing Shift Enter. And then if I want to update that later, I can only update that without without sort of running through the rest of the script. And I'll explain why that's useful in a minute. So I'll just save this as a call like plot g2.py, and we're in the same folder as the data. And now we got that name there. Okay, so now I want to actually load in the data set. So I'll just call it a name, files path, load files. So in this syntax, I'm running the function load files, and the function itself doesn't have any arguments. You can see that here, there's no arguments in the function, whereas say this one does have arguments. So we just do the empty brackets, and then what this does is just return it's a list of strings, and we assign that list this name files path. So I can run this cell now, and I want to run both cells at the same time, so I can just run the big play button. And what pops up is when we run this function, this window pops up, and it has the select files option. So you would navigate to the folder you want. Currently, I'm already in the folder, but let's say we were here. So you click through to where we want, and then select the file, and then just press open. And now in our workspace, we have this term here, files path, and we can see what that looks like. So it's a list, which is has element 1. So there's one element in the list. The list is denoted by the parentheses, and the thing that's in the list is this string denoted by the inverted commas, and the string is the file path to the actual file. So this is the name of the file, and then this is the sort of path to the file in our computer. And we know that we have that in already, so I'll separate that from a cell because I don't want to run this again, because then you have to go through the whole selecting thing. Okay, so now what I would do is actually take this path and use it to turn this data set in this text file into something that Python can use. So I would say raw data is we want to generate it from this text file. So we do np.gen from text, and then files path 0. So files path is this list of strings, and files path 0 is the 0th element of the list. So in Python, we start counting from 0 instead of from 1. And if you select that, then it just gives you this string. And then the string is input to this gen from text function. And then NumPy sort of goes through your system and opens up this file and then converts it to an array. So we can run this and then see what raw data looks like. Raw data. And now it's kind of looking like what we want. So we got an object, an array, which we can use to do calculations and manipulate it. You'll see that the first row, or the 0th row, contains two things that are not numbers. They're actually literally not a number, is the file, is the sort of type that Python saves that as. And that's because in the raw data, that's the column headings. So these are strings, and NumPy kind of assumes that we're doing everything with numbers. So anything that's not a number, it would just return as this thing. And when we come to actually plot this stuff, or we want to plot this stuff, we can't really make use of this. And the way we can do that is to just select the part of the column which doesn't contain that. So I want to create some new variables, which are each of these columns. So the first one I'll say times, and I'll define times as being a subset of the raw data. So you go raw data, which has some number of columns and some number of rows. And the one that I want is everything from the first column, the first row. Actually, yeah, so that should be rows, columns is the order. Remote control is the way I kind of remember that, but often I forget. So the rows we want is everything from the first row to the end. And the first row is this one. So the 0th row is this row, and the first row is this row. And so we want everything from the first row all the way to the end. So that's this syntax is 1 colon end. So actually the end is -1, but we can just get rid of that and include everything. And then the column, I want the 0th column. So the column goes 0, 1, 2, 3, and so on. And for the times, I just want the 0th column there. And then similarly for the counts, we can do raw data, everything from the first row onwards, and then now it's the first column here. And now that will take things from the raw data and split them up into these two different things, and now we can plot them to see what it looks like. So the plotting syntax is from the matplotlib library. We'll do plot. The sort of horizontal axis data is our times, and the vertical axis data is the counts, and I'll do Shift Enter and see what that looks like. So in the console here, it's produced this plot, and we can see that this is literally the most basic plotting form of what the data looks like. So on the x-axis, we have these numbers that are in sort of tens of thousands, and the y-axis, we have numbers in sort of the hundreds. And if we look back at the data, we can see the times are in picoseconds and the counts are in kind of hundreds. So one thing I'll do is just convert from picoseconds to nanoseconds. And the way I can do that quickly is just to divide this thing by 1,000. And then we'll see that now these values are in nanoseconds. And while we're at it, we can put some labels on this figure to make sense of what these numbers represent. So we can label the x-axis as being times with units of nanoseconds. And the label needs to be in a string. So the inverted commas here, the quotation marks define the string. And then similarly, the y-axis label, we can call it, so this is it's the autocorrelation. We haven't normalized it yet. And you'll see this is often sort of written like g to the power of 2 as a function of t. And if we were to do this now, it will kind of literally have that g caret 2 thing. And this is not that nice to look at. If we want to plot this in a paper, we can make this look a bit prettier. So one thing I'll do is I'll call the times tau, and the way we can do the actual symbol for tau is to use LaTeX. And the way that we can tell this string that it wants to be rendered in LaTeX is to just put an R in the front. And so I'll put the LaTeX stuff goes in $, is enclosed in $. So tau like that. And then in this one, we can go and use the full power of LaTeX. So we'll put some brackets in there. And then this thing is going to be tau. And then I need to wrap this whole thing in $. And the units of this, we can just, for the time being, put it as arbitrary units. So let's plot this, shift enter to plot. And now we can see that the exponent is working there. And then we have this nice sort of Greek symbol tau, and that looks pretty presentable. One thing I noticed now is that the default range of the y-axis is from 40 to 160, which is the range of the data that we've got. But for this, we want to see like what's the purity. So I want to have this value be 0. So I can set that using the y limit from 0 to in this case we can see that it's kind of 160. But in general, I don't know what the maximum of this data set is going to be. So wouldn't it be nice if there was like a way to automatically do that? And sure that enough there is, so we can just do like, instead of writing the number, sort of hard coding it, we can go max of counts like that. And now this will take whatever the max is from this data set and set it to be the maximum of the range of the y-axis. So we can press shift enter again to plot this. And now we can see it's kind of starting to look like something that sort of gives us a bit more information. Yeah, that's looking pretty good. So now what I wanted to do to make it kind of look a bit more like this, where we have the maximum is at 1, I'll do a kind of simple normalization method. And we should have an article on the wiki that kind of goes into the detail of when this is fair to use and when it's legitimate and so on. But for this purpose, I'll just do it, and then there'll be some articles elsewhere discussing when it's appropriate to do this. So basically, I'll assume that the counts over here correspond to uncorrelated events, and so we would sort of expect that when we normalize this, that the values up here will tend to 1. Basically, what that means is we want to use the data in these ranges far from tau equals 0 to define the sort of region that we expect to be normalized to 1. A way we can do that is to take all the values here and sort of take their average and then divide the whole data set by that average. So one thing I'll just do to check sort of how many I want is to look at the length of this data set counts. So I'm going to do len for length counts, and it tells us that there are 1,000 data points from here to here. We can also do counts dot shape will tell us what shape this object is, and it's a 1,000 by 1 vector. So for these purposes, I'll assume, so we got like maybe 500 here, 250. So I'll take maybe the first 100 points, and we can just check what that looks like. Let's see, plot times from the 0th element to the 100th element, and counts from the 0th element to the 100th element. So you don't need to put the 0 there. It's implied. And then I'll see what that looks like. And you can see it's kind of, we haven't sort of reached the dip yet, so it's just a double check. So I'm going to take the average of all these numbers and then divide this data set by that. So can we do that? So let's do counts equals counts divided by the average. So we take this mean function from the NumPy library, counts the first 100 values. So this is a subset of this data set containing 100 elements, and that's these 100 elements. And we're taking the mean of that and then dividing the data set by that mean. And when we press Shift Enter, this value here should be close to 1. So let's do that. Yeah, and so that's what we see here. So we've averaged all these data and divided this whole data set by that number, and then we get this thing. So now we're looking at something that is what we kind of see in papers when it's been normalized. So we can maybe even say normalized G2 there, just to be clear. Okay, and now you might think this is pretty good, but you do this experiment and you want to quote a number, and the number is the purity. So it's actually quite often it's just the dip. So the purity is 1 minus the dip. And so we want to find what this value here is. What does it go down to? And one way you can do that is just to find the minimum of the counts. In this sense, the counts are normalized now. So this should return a number that's sort of like between 0.3 and 0.4. There we go, 0.33. And then you might say you might say the G2 is 0.3 in this case. You might say that in the paper. But another way you can do it is to take these data and then fit a function to it, and then use the fitted values of that function to get to extract this number. And so the function that you fit will look like this. It would be a very nice smooth function, but it might have it might look a bit like this. And then we can extract the value of A and the value of B. So the way I'm going to do that is to define a function. I'm going to do that in this video just to kind of as an opportunity to walk through what the function is, but ideally you would just import it from the PhD functions. So let's define a function which is G2, and the input is some data set, and the number of parameters, we're going to just have some kind of arbitrary number of parameters and call it a collection P0, and then we can start entering what we want here. So in this form, this is the sort of form of the function that we want. So we've got two main parameters. One is the purity and the other one is the lifetime. So I'll call the 0th element of this list of parameters, I'll call the purity. And then the first element, I'll call tau1 for lifetime. And then what we want is we want this function to take in these. Actually, is it? Yeah. So we want to take in these raw data and some parameters, and then actually in this case we'll be plotting it, but I'll use it to fit. So we need to define the function first. So we'll return 1 minus the purity times exponential of the data set. Actually, in this case, I'm going to call it X because it's kind of the standard way. So X is actually the domain of the data. So the x-axis data, and then we divide by tau1. So this expression here now has the form of this expression: 1 minus some number times the exponential of minus the absolute value of divided by some other number. So I'll enclose that in another cell. So I can just run this now. And now this function is sort of defined in my workspace. Okay, so let's just see what that looks like. Times, and then I can call this function here, G2, taking in times, and what's the syntax? We do 0 equals. So I'll choose like a purity of say 0.7 and a lifetime of say 3 nanoseconds. And what does this look like? Okay, I don't need that bit there. Yeah, okay. So yeah, now we plotted a nice smooth curve like that. But what we want to do is take these data and fit it to this function. So for that, we need to import one more thing from scipy.optimize import curve fit. So curve fit is the function that is commonly used to take a data set and fit it to some predefined function. And so now the syntax for that, actually I'll shift enter this. So now we've imported this function, and then down here I'll start doing the fit. So the way that we do that is to define the fitting parameters and then the fitting covariances. Fit. Okay, now this syntax is the function that we want to fit, the x-axis experimental data, the y-axis experimental data, and then the parameters. So we'll fit using the G2 function that we've defined here. The x-axis data are times here, and then counts is going to be the y-axis data. And then 0 equals. So we can give this function some initial conditions in an attempt to sort of fit it. It's done using the kind of least squares fitting method, I guess. So if you can give it some values that are close, then it will sort of do it quicker, or it'll do it at all. Sometimes it'll not converge and it'll sort of tell you that it can't fit. So I'm going to look at this and say, you know, the purity is about 0.6, say, and then the lifetime is sort of maybe 5 nanoseconds. So 0.6 for the purity and 5 nanoseconds for the lifetime. And what this is going to do is return 2 of these. I won't talk about this one in this video, but this one here is going to be a list or an array of these values, which the values that give a form of this function that is the closest fit to the data. So let's just do that. And then if we print what this is, we can see that it consists of an array of 2 elements. The first one is 0.6-ish, and the second one is 5 point something. So I guess my guess was pretty close. So this value here corresponds to the purity of the function that best fits this data, and then this one corresponds to the lifetime of the function that best fits this data. And you kind of see that back here. So the 0th element is the purity. So this is the 0th element here, and then the first element is the lifetime. Okay, so then how do we use this? How do we use these 2 numbers to plot a nice sort of smooth line on this plot? And the way I usually do that is to define a new data set, which is the fitted values. So we can call it counts fit. And what we want to do is take the G2 function with times as the input. So times is the x-axis data. And then we can use these fitted parameters as the purity and tau. So I can't really remember why we put the asterisk there, but I'll double check that and maybe write a note for this entry. Okay, so now we've got a fitted array which should be nice and smooth. And the way we can sort of plot that at the same time is just to make another plot. So plt.plot times and counts underscore fit. So now if we shift enter, we should see a figure with this scrambly blue data set and then an orange, really nice, smooth fit. And sure enough, that's what we get. Yeah, so this looks pretty good, and this is probably good enough to put in a paper. And there's a few more things that I'll just add in just for the sake of this opportunity to sort of demonstrate some more functionality of this plotting and ways you can convey some more information. So one thing you might want to do is to present on the plot what these data sets mean. So we can put a legend basically. So we can define the labels of the legend like so, and then this one's going to be the fit, and then down here we can just say that the legend, display the legend. And it's gonna, if you don't have any arguments here, it's just gonna put it where it thinks it's less cluttered on the image. But you can define it to be putting to live sort of anywhere on the image. Another thing you might want to do is to put a line at 0.5 to sort of convey even more powerfully that the div does go below 0.5. And one quick way to do that is to do so we want a line, and a line is composed of 2 points. So we want to define a point here and then a point here, and then it'll just plot a line between those two. So on the x coordinates of those 2 points are going to be sort of the minimum of the x data set and the maximum of the x data set. So we can have an array which is the min of times and the max of times, and then the y data set is going to be, or the y values of the 2 points are going to be the same. It's going to be 0.5 here and 0.5 here. So 0.5 and 0.5. So let's see what that looks like. And it's just drawn a straight line there. And we can see that the div goes below that. So that's a nice illustration. You might want to change the color for the line style. So we can change the color using the color parameter. And I think if we just write in like that, it should, yeah, okay. So that's a way to sort of hard code the color. And then you can imagine putting any other sort of word here that's the name of a color. Another way to do this is to define the line style with the color. So we can define the line style as being black. In this sense, K is black because B is blue. And then we also want it to be dashed. And then we can have a dash line there like that. Maybe this is a bit too bold, too kind of sharp. So we can change the line width to say 1. I think the default is 2. And now it looks a little bit thinner, which is kind of a bit more of a subtle touch. Okay, so one more thing you might want to do is, there's kind of a lot of free space here. We can sort of put some stuff. One thing you could do is to put down here, say, the actual purity or the G2 dip at 0, and also the lifetime. So let's do that, and we can annotate this graph in that way. So we can do just annotate, and now the syntax here is we want to first put in the string of what we want to appear, and then the XY coordinates of where we want it to appear, and then some extra arguments like the color. So let's do the string is going to be, I'm going to use some LaTeX, so I'll put R there, and now I'll say let's call it tau. It's going to be LaTeXified equals something. So now this is a string, but we want in the string to be the value of we want this number here, this number actually for tau. So how do we do that? We put a placeholder in this string thing. So we put a percentage sign and then the type of thing we want to replace with that percentage sign. So if it was a string, then we would put S. If it was an integer, we would put D. But in our case, it's going to be a float or a real number. So we're going to put the number of decimal places we want and call it a float like that. And then we're going to say in place of that percentage sign, we'll put the lifetime, which is stored in this this array POPT, and it's the first element after the 0th element. Okay, so now where does that go? That goes in some XY coordinate position, and let's just say it's going to be at sort of 20 and I don't know, 0.4 looks pretty good. So 20, 0.4. And yeah, I think so. It's going to be, I think it'll default print as black. So let's just see what that looks like. There we go. So we got the tau, the nice sort of Greek symbol tau. Actually, let's call it, because we've got tau here, so we don't want that to be the same tau. Let's call it _1. So tau 1 is pretty common notation for lifetime, or capital T1 maybe. So now we got a little subscript there. And actually, let's put units in this. So we'll do nanoseconds. Now we've got nanoseconds there. So it looks pretty good. And then maybe below this, we can do, I'll just copy this line. And we want to do, say, the purity. So we'll do, actually, I'll copy it from here. G2 at 0, tau equals 0. And now it's going to be the 0th element of this of the fitting functions. Remember the 0th element is purity and the first is the lifetime. And we don't want it to plot on top of this one, so we'll do down a little bit, maybe 0.3. So that should plot sort of just here. And that's the units are, let's not do units for this. Shift enter, and yeah, so we got oh, actually, yeah, okay. So the way that I've defined this function is in terms of purity, but obviously the number that we quote is the actual sort of rise from 0 to that number. And so what we want here is actually 1 minus the purity. What is that? 1 minus the purity, shift enter, and now we got 0.398, which is the distance from 0 to the minimum of the orange curve. That's what this number is. Yeah, so I think that's a pretty good place to stop. Actually, one more thing I'll do, because I imported this save figure thing. Let's save this figure. We've gone to all this trouble to produce this nice plot. Let's save it in the folder where the dataset lives. So you'll remember that the files path is a list, and it contains file paths. So the 0th one is the path to our dataset, and we can actually use this to define where we want to save the figure. So you'll notice all this information here contains file paths that go to the folder that our actual dataset is contained in. And we can save the figure in that folder using the save figure function. So the input is the file path where the data set lives, and then whatever you want to call the file, the image, the saved image. So let's do save figure. Files 0, and I'll call this it'll have to be a string for the file name. Call it sort of G2 plot. So ideally, this is going to save this image as a PNG type into this folder with the name G2Plot. So let's do Shift Enter. So currently there's no image in here, and we'll do Shift Enter, and it'll sort of plot this again in the console. And then here you'll see now this image has appeared in the folder that this data set is contained, and it looks like that. And we can click on it. And yeah, so it looks pretty good. Yeah, one thing we could do is maybe change the size of the figure by defining the size like this. Fig size equals, and I think this is it's the dimensions in the X direction in inches, I think, and then in the Y direction. So maybe a good size is like 10 and 6. Shift Enter, and now we go to bigger plot. One thing that sometimes happens, especially with doing subplots, is that these labels will get cut off in the image. And one thing I found that's helpful for that is just to do site layout like this, and it will just kind of fill up the actual size of the figure with your information, and it's a bit more neater and cleaner. So from here you might want to define these numbers according to, say, common widths in papers, like column widths and heights and so on. But now you know how to do that. So that's all there. And yeah, I think that's a pretty good place to stop. So if you have any thoughts or comments, post it in the Slack, and hopefully this is helpful for you.